Hey, good afternoon, folks. Steve Cat5JUF. Got a video today. I'm going to go over some log problems that you are going to see in the Technician, General, and Extra. What I did was I went through and extracted all the log related problems from the test pool and went through and I'm going to solve all of those today for you. And we'll go through and, of course, do the log problems. If we have time, we'll look at some radio coax efficiencies, and then lastly, we'll look at some log curves. In your ham radio career, you're going to come across primarily two log formulas that you're going to need to become familiar with, and that is the first one is A, which is if you have the decibels available in the situation and you can calculate the power factor, which can be a positive number of the power factor of 1.26 is a gain, a power factor of 0.794 is a loss. So that's how they calculate the power factor. So if you have 100 watts of antenna gain of 1.26 is going to give you effective radiated power of 126 watts. Same thing on the coax. If you've got a minus 1 dB at say 100 feet, you put 100 watts through the coax, you're going to get 79 watts through at the end of the coax. The different one is if you have two units, for example, the problem says you've got 100 watts coming out of the antenna, but you've only got 50 watts at the end of the coax being measured. Well, that's of course, that will give you a minus 3 dB. So that's the other problem that you're going to need to become familiar with. In short, they call this one anti-log. This one here, they call this log or log base 10. And all your logs in ham radio are going to be log base 10. So you won't have to worry about dealing with any of the other log bases. These are the buttons here you're going to use. So what you'll do on the TI-30, which is what I'm using, you would press the second key first, and then you would press the log key, and that's going to give you this little guy right here. Same thing on this one here. If you press the log button here on your calculator, it's going to give you this right here. Now when you see the on the screen, you're not going to see the 10. It's by default, it's going to be a log base 10. All right, let's go ahead and work some problems. These are from the technician pool. So what you have here first is let's clear the calculator. And let me check something real quick here. We are in degree and all that looks good there. All right, so what we're going to do first is we're going to do this problem, and it says what decibel value most closely represents a power increase from 5 watts to 10 watts. So the way we would do that is we would type 10 log, and then we would put 10 on top, and we would click the numerator denominator button, and we would put 5 on the bottom, and then press enter, and that's going to give us our answer of 3.01 dB. So that's how you do that problem there. All right, let's clear the calculator and we'll go to the next one. Now it says which decibel value most closely represents a power decrease from 12 watts to 3 watts. So that's power loss, so that's going to be a negative dB. So again, we're going to go 10 to the log base of 10, and we're going to put 3 on top, which is the measured value, and 12 is the reference, and that's going to give us a loss of negative 6.02 dB. So that's how you solve that problem. All right, the next problem, it says which decibel value represents a power increase from 20 watts to 200 watts? Well, that's a gain, so that's immediately we're going to go ahead and again we're going to do the 10 log, and the measured value is 200, and the reference value is 20, and that's going to give us a gain of 10. So that's pretty cool. So those are the 3 questions from the technician pool. All right, now we're going to go to the general pool. This one here is asking what dB change represents a factor of 2. So a factor of 2, increase and decrease. So if you increase, you're going to multiply times 2. If you decrease, you're going to divide by 2. So simply it wants to know a factor, a dB change. Doesn't necessarily, it's just it's asking negative, positive, but we'll go through and show you. At the end of the day, the answer is 3, but here's how you do the problems. So if we have a gain of 2, we're going to be 10 log. And we're going to be 2 is the measured value, 1 is the reference value, and we have a gain of 3.01 dB. Now for the decrease in power, we would do 10 log also, and we're measuring 0.5, and the reference is 1. That's going to give us a value of, you know what I forgot to do here? Let me redo that. 10 log 0.5 divided by 1. There we go. Now we have a negative 3 dB. So you see here the answer is 3, but that's how you get to both of these. So if you have a measured value of 1 on both situations here, your measured value is 1 here and it's 1 here, or excuse me, your reference value, and the value says a decrease of 2. That's what you're measuring, and if you divide it by 2, that's what you're measuring also. That kind of goes back to that formula that we looked at earlier. All right, let's clear this off. Now the next question in the general pool is decibels are always represented in 100 feet segments. So most all coax I've looked at, DX Engineering, most everywhere it's 100 feet. So that's the answer there. So that was easy to remember. Just remember decibels since that's what you're dealing with. All right, now the extra pool, this one's a little different. We've got a couple of things going on here. We've got a couple of losses, and then we've got a gain from an antenna. So everything on this question here is relative to a dipole, and that's going to be important. But the simple thing is all you have to do is take all your negative numbers and combine them, and then take all your positive numbers and just take the difference. And what you're going to end up with is you're going to have a net gain of 2.8. So what we would do then is we would take, we're going to do the anti-log here. So we're going to do second log 2.8 numerator denominator over 10. And that's going to give us a factor of 1.91, and we're introducing 150 watts, so we're going to go times 150. And that's going to give us 285.82 watts, and our answer is 286 watts. So that's how you deal with this. So again, like I was saying, you take your negative numbers and you get all that situation worked out. And then you take your total negative number, which is 4.2, and you compare it to the gain from the antenna, and the difference you get is the 2.8. So that's what we use in the problem. All right, let's do another one. Same thing going on here, except we got a couple of more losses going on. We've got a 4 dB line loss, 3.2 duplex, and a circulator loss. And of course, all those added together gives us a total loss of 8, and our gain from our antenna is 10, so the change is 2. So that's a 2 dB gain. And again, it's DBD. Again, everything's referenced to a dipole in these questions, so everything here is straightforward. All right, so now we'll do the math. We'll do second log 2.0 numerator denominator divided by 10. That's going to give us a multi-factor of 1.58, and our power is 200 watts. That's going to give us 317 watts at the antenna, effective radiated power. All right, so that's how we do that one. Okay, now it wants to know how much does an antenna have compared to a half-wave dipole. So that's a key statement right there. Compared to a half-wave dipole. You need to remember that. Put that in your memory. The reason is because it's saying that the antenna we're comparing has a 6 dB gain over an isotropic. So those are some key things there we need to pay attention to. What's going on here is the isotropic antenna, this antenna that we're comparing, has 6 dBi gain over an isotropic. So that's the line right there. That's 6 dBi gain over an isotropic. But it wants to know what it's compared to a dipole. So let's figure out what the dipole's doing. All dipoles typically have about 2.15 dBi gain built into their inherent design over an isotropic. So we're going to make that comparison. That comparison is going to be the answer will be 3.85 dBd, or in your answer it's 3.85. So that's how we get to that. It's asking you to compare a dipole. Is asking you to compare it to a dipole, and the dipole again already has that additional 2.1 dBi gain over the isotropic that we see here. So the comparison is it's this distance right here. So that's how that works. And of course, here's your isotropic circular antenna, and there's your dipole antenna right there. The dipole has the same power. It's both are still 100 watts, but why you get the additional gain on the dipole antenna is because the positioning of the dipole antenna, the radiation pattern, instead of being a circle like the isotropic is, what you end up with is you end up with these patterns that look something like this, and you get this extended reach over here. This extended reach outside or above what the isotropic is. Same thing here, you get the same reach on this side here, above what the isotropic is. So that's where you get the 2.5 dBi. So over in this area here, for example, you're not getting that much power. You're not getting that much power from the dipole, because this power that was here is actually been squished into this area. Same thing here. This power right here has been pushed out in this direction. It's still 100 watts, but it's just condensed or squeezed a little bit in making it go further. Think of it like a balloon. If you squeeze a balloon, it's still the same volume of air, you're just repositioning it a little bit. All right, so that looks good. So let's do a couple of problems here and then we'll wrap it up. We've got a coax loss here of minus 4 dB at 150 megahertz for 100 feet. So we're going to do shift log, try to get you in where you can see that. Minus 4 over 10. That's going to give us roughly 3.98 times 100 watts. That's going to give us 39.81 watts at the base of the antenna. So that's a typo right there. That should be 39. This is actually my bad. This should be 39 watts. I didn't fix the slide, but that's what we got here. It's 39 watts. And so that's how you do that. We'll do another one here real quick, and then we'll wrap it up. This one here is got 2.2 dB, so let's do the same thing again. Second shift log, negative 2.2 over 10 is going to give us 60 times 100 watts. That's going to give us roughly 62 watts here at the base of the coax. So those are two examples on how you do coax efficiency. And that's part of what you're going to be learning when you're doing logs. You're going to learn how to understand when they talk about gain, antenna gain, dBi, dBd, coaxial loss, all these things. You're going to be able to equate these to real losses or values, factors. All right, let's do this. That pretty much wraps it up. This is the log curve I wanted to show you real quick. This is logs going up. So that's the log going up. 3 dB has a 2 times factor, 6 dB has 4, 9 dB has 8. This is the logs going down. Minus 3 dB is a half, minus 6 dB is a quarter, and minus 9 dB is an eighth. And you can kind of see, over here, you can see the losses. So if you want to look at some numbers here, that's what you can see. You have how much power is getting through the coax in this column here. In this column here, it shows you how much loss. All right, again, mainly you just need to know the two formulas. And once you know those, That'll get you through log. So I hope this helps. Thanks again. Appreciate you watching and have a good week. Thanks again.